Quantum computing is the most overpromised technology in the room, and Kronos works on it anyway, but with our eyes open. So let me tell you what it actually is, what it might one day do for fusion, and the one honest verdict we will not soften. There is no quantum advantage for us this decade, and we say so out loud. Start with the unit. A classical bit is 0 or 1. A qubit can be a blend of both at once, a superposition, best pictured as an arrow pointing anywhere on the surface of a sphere. That richer state is where all the promise comes from, and also where all the fragility comes from. The real power shows up when qubits entangle. Entangled qubits are correlated in a way that has no classical picture. Measure one, and you instantly know something about the other. With entanglement, a modest number of qubits can represent a state space so vast that no classical computer could ever write it down. That is the theoretical prize. You compute by applying quantum gates, operations that rotate and combine qubit states fired in sequence like a circuit. String the right gates together, and you have an algorithm. It looks a little like ordinary logic, but every gate is steering probability amplitudes, not flipping switches. Then you measure, and this is the catch. Measurement collapses the superposition. All that rich parallel state resolves to a single classical answer, chosen by probability. So a quantum algorithm is really the art of arranging interference so that when you finally look, the right answer is the one most likely to appear. For the problems fusion cares about, the quantum behavior of electrons in materials, the leading near-term method is the variational quantum eigensolver, or VQE. It is a hybrid. A quantum computer prepares a trial state. A classical computer adjusts it back and forth, hunting for the lowest energy. More exact methods exist, like quantum phase estimation and direct Hamiltonian simulation, but they demand hardware we do not have yet. And that is the crux, because hardware is noisy. This is the NISQ era. Noisy intermediate scale quantum. Qubits decohere. They lose their delicate state in microseconds, corrupted by the faintest disturbance from the outside world. Every gate you add injects a little more error. Run a circuit too long and the signal drowns in noise. The known cure is quantum error correction, spreading one reliable logical qubit across many physical ones, so errors can be caught and undone. It works in theory, but the overhead is staggering. A single logical qubit may need hundreds or thousands of physical ones. We are not close to the scale that requires. So we do the unglamorous, decisive thing. We estimate resources. For a real fusion chemistry calculation, how many logical qubits and how deep a circuit would it actually take? You run those numbers honestly, compare them to what exists and what is credibly coming, and the gap is not small. It is orders of magnitude, which brings us to the crossover, the point where a quantum computer beats the best classical method on a problem we care about. For fusion, that crossover is not here. Classical high-performance computing, the simulation stack we already run, remains the right tool for the real design work today, and will be for years. So here's the verdict, stated plainly. No quantum advantage this decade. Not for Kronos, not for Fusion. Anyone selling you otherwise is selling. We publish that conclusion alongside the resource estimates that back it, so you can check the reasoning yourself. Then, why work on it at all? Because the fundamentals are real. The hardware is improving, and the day the crossover arrives, we intend to be fluent, not scrambling to catch up. We track it precisely so we can tell the difference between a genuine milestone and a press release. Honest about